Okay, so moving on from where we left, today we'll be doing motion analysis of particles, and these particles are attached to each other through means of usually through strings, cables, and this is just a matter of this part is probably slightly hard, and it's not quite what we have done before. I don't know if you guys have done this before, when two particles are connected through strings. When you move one, and they may be connected through pulleys and so on, and those problems tend to be slightly less intuitive, and you need to do this. There's a recipe for solving this problem. So what I'll be doing is talking about how to go about solving it with examples. So I'll just start with an example, because I think that's the easiest way to teach this part. So okay, example. Okay, and I'm going to motivate this with a really simple example. This is a particle. I've drawn it to the body, but it's a particle. It can only translate, not rotate. It's connected to another particle, B, by means of a string. Okay, and the string is in what is known as inextensible, which means that it cannot stretch, unlike a spring. So if I tell you that, if I say xb, okay, is the displacement of particle b is 1 unit to the right, then it's obvious that a would move 1 unit to the right, right? So what I'm going to do is I'm going to have what I call the datum line, or this is like the, you can think of this like the origin. I don't call it the origin because it's a line and not a point. Okay, I'm going to represent the motion of A with xa. This is the displacement of A to the right. Okay, and similarly, xb is the displacement of B to the right. Okay, so as I said, it's kind of obvious to you that xb dot is xa dot, right? Xb is not equal to xa, but xb dot is equal to xa dot. That is, if b displaces or moves by 1 unit, then ba would also move by 1 unit. And similarly, xb double dot is xa double dot. Okay. Now what will happen is, this is very simple, but it gets complicated. So I'm going to show you a technique to figure out xb dot equals xa dot without really thinking about it. You don't have to think about it. You just have to set up the problem right, and the xb dot equals xa dot will just come out. And that will be useful when we go to systems where there are pulleys and strings wrapped around it and so on. So what you need to do is, we're going to exploit the fact that this string is inextensible. If the string is inextensible, then the length of the string, L, does not change, right? L is the length of the string. Length of the string is xp minus xa, right? Now, if I differentiate this with respect to time, then I would get L dot equals xb dot minus xa dot. Okay, so if the string is inextensible, then the length cannot change with time. So this is 0 because, right, inextensible string. So if xb dot minus xa dot is 0, then we can write xb dot is xa dot. Okay, and if we differentiate again with time, with respect to time, then xb double dot is xa double dot. Okay, so what we've done here is tried to express the length of the string, or the things which don't change with time, as a function of things which do change with time, which is the position of A and position of B, and that was used to find a relation between the velocities. Okay, so that is the technique we'll be using. I'll motivate this with another example. So this is the concept. Now we'll take it to a problem which is slightly more harder. And you see the real power of using something like this instead of trying to guess it from looking at the figure. Like first we guessed it was VB or XB dot is XA dot. Okay. So here's another example. Okay, so there are two particles A and B attached to each other through inextensible strings and pulleys, two pulleys. Okay, if velocity of A is VA, find velocity of B. Okay. So what we'll do here is we'll use the same technique. That is, remember, for the first question, we figured out the length of the string between the two particles and wrote it as a function of xa and xb. Similarly, let's apply the same technique here. So first thing you want to do is, before we can even specify to all that, we need to first get the datum line. So let's say that our datum is, so we could choose this as the datum, right? That's absolutely fine, but I'm going to choose this line as the datum. And the only reason is because really this length and this length will not change. As B moves down or A moves up, or vice versa, A moves down, B moves up, this distance is going to remain constant, right? So it doesn't affect if I move the datum slightly down. So I'm going to call this as my datum line. Okay. Next thing I'm going to do is I'm interested in motion of A and B. So I better draw lines from the datum line to A and B. So for B, this would be XB, and I need to draw a line all the way to A. Okay. Now I could do that. I could draw a line like this all the way here. But what I notice is that this point and this point would have the same motion, right? It would be moving by the same amount because this string is inextensible. So instead of specifying all the way down, I'm just going to specify XA to be this. Actually, you know what? Let me put YB so that you don't get confused with the direction. So this is YB because I would like to stick with Y is around is downwards, and this is YA. Okay. Okay, so the reason why I said YA here is because the motion of this point and this point, or A, is the same. Okay, so I wrote YA, YB. Okay, now I want to try to figure out the length of the cable, just like the previous problem. So the length of the cable, there are actually two cables here. There's one this over here, and the other one goes all the way like this. So the other one is so just like the previous problem, I tried to express the length of the cable in terms of XA and XP. Similarly, I'm going to try to express the length of cable. So L is length of cable or string. We call string length of string. Okay, so that is given by this part YA. It's this part. So if R1 is the radius of the circle of the radius of the pulley, then this thing is going to be pi R1. Okay, I've assumed that's R1. Then you see that it doesn't matter. The final value will not, the velocities will not depend on R. So it's perfectly fine to do that. So this is R1. Similarly, this distance is, it's going to be, what's that? What's this distance? It's YA, right? It's the same as this. Okay, then the string wraps around the second pulley, and let's say that this is R2. So it's pi times R2. And then we're left with this part, which is YB. Okay, so length of the string is YA plus pi times R1 plus YA plus pi times R2 plus YB. Okay, is that clear? Okay, so this is the key step. Once you are here, it's very trivial to get the velocities. Simply differentiation. Differentiate with respect to time. L dot is YA dot plus pi R1 dot plus YA dot plus pi R2 dot plus YB dot. Okay. Now, as you can see, the string is inextensible, so the length does not change with time. The radius of the pulleys cannot change with time. That's 0. So all we are left with is 0 equals 2 YA dot plus YB dot. Okay, so I can move things around. I can move YB on the other side. YB dot is minus 2 YA dot. If you would like to call the velocity of B as VB, then this is simply VB dot is minus 2 pi dot A is VA. This is wrong. This is VB. VB. Okay, so we found out that when the velocity of B is 1 unit, sorry, we're given VA, right? So velocity of A is 1 unit, so it's moving 1 meters per second, then velocity of B is going to be twice of that. So what we observe is that velocity of B is twice that of A. Okay, and the second thing to note is that the motion of B is in the opposite direction of A. That is indicated by the negative sign. B moves in the opposite direction as that of A. Okay, so intuitively, if you move A down, right, B would move up, right? Does that intuitively make sense to you? So the sign looks right. The velocity, it seems, I don't know, sometimes it's hard for people. You could figure this out by intuitively, but I think this part, the 2 is sometimes not very intuitive for people, especially when there are like 3, 4 pulleys, some questions you'll do for homework. So this is a very easy and generalizable way to solve problems where there are a bunch of pulleys. All you got to do is find the cables. Each cable length would have an expression for it in terms of motion of the particles, and then you'll write expressions for those and then differentiate with respect to time. Yeah.
Could you go back over the how you came up with the equation for L?
Yes, absolutely.
And L is just that length between the pulley and A, is that right?
So length is, the length is this. Okay, does that answer your question?
Yes.
Okay. So here is the recipe. Okay, so when there are multiple particles, first what you do is choose a datum line. So the keyword here is the datum line. Okay, you can have multiple datum lines, that's absolutely fine. You can have one for the x, one for the y. You can have 2 in the x direction, so that will be problem specific. So then assume variables that describe the motion of points. So that would be things like xa, xb, ya, yb. Okay. Then so assume suitable variables and also constants. This is like choosing R1, R2, L1, things which don't change with time. Okay. And then find total length of the cable or string as a function of assumed variables. So you need to find L as a function of YA, YB, XA, perhaps there'll be R1, R2, and so on. Okay, and you will have, if there's another cable, you'll have another expression. L2 is F1, F2, so you'll have similar things. So each cable you have that you have, you'll have one equation. And then this is the easiest step. Differentiate once to get relation between velocities and differentiate twice to get acceleration. So this is the most easiest step, provided you got 1 through 4 right. Yeah?
Now the radius isn't going to change, and we know it's 0. Do we have to write that out?
No, you don't have to write down. So in fact, as I go forward, I will not even write R. I just skip R. So what he asks is, do you have to all the time write this? It doesn't really matter, right? It eventually disappears. So in future, what I'll be doing is, I'll say L is YA plus YA, this plus this plus this, and I will not even say, plus this, and I will not even add pi R1 plus pi R2, because that doesn't change with time. It's assumed that you figured that out and you don't have to write it down. All I'm looking for is writing L equals, so a perfectly fine way to write this would be L equals YA plus YB, absolutely fine. Okay, so based on this, let us do some harder problems. Okay, so if the end A of the cable is pulled down with a speed of 2 meters per second, find the speed at which block B moves. Now, somebody suggested that I should post this notes before I come to class. I did post that. Did you guys get a chance to look at it? So I'll try to do that every class. Hopefully I'll do it every week so that you have it before the class. So if you print that out, then you don't need to take notes. You can just start filling just solving it on the paper instead of writing things down. But that was a good suggestion. If you have any suggestions, just let me know. Okay, so what we'll do is we'll follow the same recipe. I do this twice because I want to work with the second figure. Okay, this is just for helping me solve. Okay, so I can take the datum to be here, but what I observe is that if I move it right here, it won't really change anything because this distance is going to be constant. It's not going to change with time as the system moves, right? So that's going to be my datum. Okay, the next thing is we want to find the motion of B as a function of A. So let's just draw YA and YB. So YA is motion of point A, YB is motion of point B, but what I do is instead of trying to draw an arrow right to here, I will draw it right over here because I observe that this point and this point would have the same motion, right? Would be the same because the link connecting this point with that point is rigid. It cannot stretch or compress. So this is going to be YB. Now, one more thing to note is that unlike the previous problem, there are two cables. There's one cable like this, and then the other one is this way. Okay, so I can for sure, it may not all be the case always, but most likely you'll end up with two equations because there are two cables wrapped around. So let's try to write an expression for the length uh, of the first cable which I just drew. So let's try to write the length of this one. So solution length of, I'll call that ADC. Okay, so I've still not defined other variables, okay, but they'll become obvious when we start trying to write an expression for length. So there is YA. So this is this part. Then I need to find this distance, but I don't have a variable which defines that distance. So let me create a new variable. Let me call it YC. I call it YC because it's going to give me the motion of point C. This is point C. Okay, this is YC. So YA is this, YC is this. Again, there'll be another YC. So it's YA plus 2YC. Okay, I've totally skipped writing pi R1, pi RD if you like, and pi RC because as you notice that will not come eventually when I differentiate. So I'll just skip that. So YA, this is YA, this is YC, YC, 2i's YC gives me the length of ADC. Okay. Similarly, I can write length of CB, and let me call this point, it's called E. Okay, CBE, length of CBE is going to be this distance plus all the way this distance. Okay, so the easier one is the second one I drew. This one, it's just YB. Okay, what is this distance? So it's YB minus YC, right? This distance is YB minus YC, so YB minus YC. So let's differentiate 1. So I have 0 equals ya dot plus 2yc dot, which means that yc dot, the reason I'm writing in terms of yc dot is because I'm not interested in the motion of yc. I would like to eliminate that eventually. And then differentiate 2. 0 equals 2yb dot minus yc dot. So yc dot is twice yb dot. Okay, so the last step is put 3 in 4 or 4 in 3 to get 2yb dot equals minus half ya dot. Okay, so yb dot is minus 1/4 ya dot, or in other words, vb dot is minus 1/4 va dot. And I think in the question you're, what's that?
It's only VB and VA.
Oh, my bad, that's no dot. Good point. Sorry about that. Yeah. Okay, so you're given that the velocity of A is 2 meters per second. So VB is minus 1/4 times 2 is minus half, which is 0.5 meters per second. Okay, so what this is saying is when A moves down by 2 meters per second, right? When you pull it down, B is going to move up, and the reason for that is it's the value is negative of A by half meters per second. So what you can do with pulleys, what this is showing is that you can amplify or de-amplify the motion. A unit motion in A will cause 1/4 of the motion at B. Okay, so that's what pulleys help you to do. In fact, later on when we do forces, you'll see that you can also do the same with forces. The force at A is going to be actually 4 times the force at B. So you can amplify or de-amplify the force. Okay, but that's something for later. Okay, any questions on this? Yeah.
Why is it 2YB and step 2?
In step 2, so it's YB plus YB is 2YB. Oh, Y, okay. So let's look at CBE. CBE is, C is this, B is this, and E is there. So this point. So then it's this cable, which is this length, YB, first one. And second one is this length, it's YB minus YC. So that gives you, yeah, maybe I should draw it here. This is better. This is YB minus YC. Okay. Yeah. So if you want, if you find it hard, just redraw the figure, no problem. Write things down, and it's much easier if you have things down on paper. Can easily see what it is. Any other questions? Yeah.
By A and by C is equal. They shouldn't be equal by A and by C. It seems to me that
YA should be equal to YC. So, okay, so in this figure, it's kind of deceptive. It looks like YA. So she's saying YA and YC look like they're the same height. So should we assume YA equals YC? And the answer is no. It's because at this instant of time, they are close by. But after a few seconds, YA will be up and YC will be down, and that assumption will not hold true. So when you're solving for these problems, you have to take the general case, not the specific case when they're close by, because you're told to find the general velocity, not at that particular instant. Okay. Okay, so we'll use the sort of the algorithm I gave you earlier. First, we have to identify a datum line. Before that, let's think about how many cables are there in this case. How many cables do you see? Or strings? There are two, right? One is from A to D and over here, and the other one goes from D, C, all the way this way. Okay, so what this is telling me is that there will be two equations eventually. Okay, so let's say that the datum is, well, we could put the datum over here, but I think it doesn't hurt to put it over here. And that's because this length does not change when the whole system moves. Okay, so once I have the datum, I'm interested in the motion of point A and point B. So I'm going to specify that with xb for point B and xa for A. Okay, and so just because there'll be two equations, I can tell you with certainty that you need to assume there'll be three variables you need to assume, just like the previous problem. Remember, we had defined motion of A, B, and C. In this case, C is here, so that doesn't move, but this point does move. So this is xd. Okay, so I've sort of run this problem many times, so I know that you need to specify xd. But when you start writing the lengths of the cables, if you're not known this, when you start writing L for each of those cables, you'll figure out that you would need another variable, and that would be d. Okay, there's no other way to go ahead and solve this. Okay, so I've set this up. Now, am I missing something? Do I need to specify anything more? You mean this one? Yeah, I need to specify that. How will I go about specifying that? So let's call this point E. So L A D E is this length first. So that's going to be, so what's this length in terms of whatever I have on the board? XA minus XD, that's right. So this is obviously XA minus XD. Okay, I need to find this length. How do I do that? I don't have variables to define that length right now, right? I know what this distance is. It's what? It's XA minus XD, but I don't know what this distance is. And there's nothing here in this figure which I've drawn which would help me do that. But do I know something about this system which may help me to define another variable? So what's the distance between E and C? This distance. Can I say that this distance is constant? Right? Because when the A moves, B would move, but the distance from E and C will not change. Do you see that? Okay. So I create another variable. This is not related to length of any of those cables. And this is something new. We've not done this so far. Okay. Sometimes you might have to find distances which do not change with time, like this one. So once I have D, can I now try to write length of this cable? It's this length. So this thing is D and this is XD. So can I write this as D minus XD? I cannot write it in terms of A. Somebody said, can I write in terms of A? I cannot, because when A moves, this distance will change, and then I have no way of specifying the remaining distance. You can try to specify in terms of A, but you'll see that you cannot do that. Okay, it should hold for any when A moves, that whatever expression you write should hold for any location of point A. Okay, this is the only way you can do that. So this is xa minus xb plus d minus xd.
Shouldn't it be XA minus XD?
Oh yeah, xa minus xd. That's right. I wrote it here to xd. Sorry. So this is d plus xa minus 2xd. Okay, so let's just differentiate this with time. So with respect to time, so 0 equals d dot. So the rate of change of d is the distance is going to be 0 plus xa dot minus 2xd dot equals 0. So xd is half of xa dot. Okay, so that completes length of ADE. Next, we need to find length of the other cable. So D, C, and let's call this point F. DCF. So that's going to be this distance, which is simply XD, plus this distance. So what's that distance?
XB would go to the fully.
Yeah, so okay, so what I could have done is to make my life easy. This is fine, but I think I should have actually drawn this not till here, till here. That would have been much easier. So the motion of this point and that point doesn't differ, right? It's going to be the same. So I'm going to change that. So instead of specifying this distance, and that doesn't change anything here because I've not used xb so far. I think this is a better way to specify motion of b. So now I think I can write that as so this distance
Professor, that DCB or DCE?
DC, I wrote it as f, DCF.
Oh,
Yeah, so that's going to be xd first part. This part is going to be simply xb. Okay, I know that there's this part, but well, sorry, that's not my bad. So it's really xb, sorry, and then plus this part, which is again xb. So this is going to be xd plus twice xb, and so differentiate with respect to time. I get xd dot plus 2xb dot equals derivative of dcf, which is 0. So xd dot is minus 2xb dot. And so if I put 1 in 2, put 2 in 1, I get minus 2xb dot is equal to half xa dot, which means that what am I told to find? I'm told to find if velocity of A is given, find velocity of B. So velocity of B is 1/4 velocity of A, and so VB is minus 1/4 VA, and VA is 3 meters per second. So 3, so it's minus 0.75 meters per second. Okay, which is saying that if A moves to the right, then B will move to the left. Okay, that intuitively makes sense. So I'm out of time, but there was another problem I wanted to solve. I will solve this and post the notes, but I would recommend that you try this by yourself.